Hi friends, in this module we are going to learn about the oxidation states of actinides. Now, first of all, if you will see, the oxidation state is the net numerical charge present on an atom of an element in its combined state. This is also known as oxidation state, or simply we can say as oxidation number. Now in case of F block element, all the elements are metals, and metals have tendency to donate electron, lose electron, and because of this tendency these all elements shows positive oxidation state. If you will see the general electronic configuration of F block element, so it is N-2 F1214, N-1D021 and Ns2. In case of actinides, all actinide elements shows common oxidation state of +3. Now this +3 oxidation state is achieved by loss of one electron from the penultimate shell, that is 6d orbital, and 2 electron from the valence shell, that is 7s orbital. But along with the +3 common oxidation state, element can also show higher oxidation state of +6 and +7, which is compatible with the transition, or I can say D block element. Now if we are considering the actinide series, which actually start after actinium from thorium to lawrencium, this series of 14 elements, so you can see all these elements can exhibit +3 as a common oxidation state, and this common oxidation state is similar to what lanthanide also. It is due to availability of 5f, 6d and 7s orbital, where loss of electron gives common oxidation state of +3. So we can see from actinium to lawrencium, all these elements are exhibiting common oxidation state of +3. But if you will see, in case of actinium, thorium and americium, they are exhibiting +2 common oxidation state, and the +2 common oxidation state compounds are iodide, sulfide and bromide. Can I say thorium iodide, thorium sulfide and thorium bromide? As the atomic number increases, the +3 oxidation state goes on becoming more and more stable. Thorium, protactinium, uranium, neptunium, plutonium, americium and curium also exhibit +4 oxidation state. If you will see, from actinium to berkelium, these all elements are exhibiting +4 oxidation state. Now neptunium 3+ and plutonium 3+ get oxidized to neptunium 4+ and plutonium 4+. I told you element in the lower oxidation state act as reducing agent, and the element in the higher oxidation act as oxidizing agent. So europium 4+ and neptunium 4+ are very stable as they are acting as oxidizing agent, but berkelium in +4 oxidation state is oxidizing agent, but it is more stable than curium 4+ and americium 4+. This is due to the half filled f orbital configuration, that is F7 configuration. Now if you will see, from thorium to americium, all these elements are exhibiting +5 oxidation state, but from uranium to americium, if you will see, oxidation state value increases and that reaches to what, +6. But about +6, if you will see, the actinide series actually exhibiting higher oxidation state, and this is compatible with the D block element, that is transition element. So this exhibition of the large number of oxidation state of actinide is supported by the fact that there is very small energy difference between 5f, 6d and 7 subshell. That's why the electrons can really participate for the bonding from these corresponding orbital, and that's why they have stronger tendency to donate large number of electron, and that's why they all have higher value of oxidation state like transition element. If you will see, 7, which is the highest oxidation state exhibited by neptunium and plutonium, and the 7 oxidation state exhibited by manganese in the D block element. So the actinides also have the higher oxidation state. If you will see, +6 oxidation state is exhibited by uranium and americium. So I can say there are certain elements which show very high oxidation state and can form more number of complex compound due to this. As oxidation number increases to +6, now the actinide ion are no longer simple. Since the charge density, nuclear charge increases, they form oxo ions, that is also called as oxygenated ion, as in case of europium and neptunium. That's all in this model. Thank you very much.